There is a lake I want you to imagine. For years it is clear. You can see straight to the bottom, the plants, the fish, a calm green world under glass. Every summer a little more fertilizer washes in from the fields around it, a little more each year, and nothing happens. The water stays clear. The lake looks fine. It looks fine for a very long time, and then one spring it isn't. In the space of a few weeks the water turns green and stays green, thick with algae, the bottom gone, the old clear lake simply not there anymore. Nothing new arrived that year. The last bit of fertilizer was no bigger than the bit the year before, but the lake crossed a line and it snapped. This is the strange thing about complex systems. They do not always bend in proportion to what you do to them. You can push and see almost nothing, and then one more small push and the whole thing jumps to a completely different state. A forest becomes a grassland, a coral reef becomes bare rock, an ocean current switches off. The pressure builds slowly and invisibly, and the change, when it finally comes, is sudden. So here is the question this video is about. If the warning does not show up in the state of the system, if the lake looks clear right up until the week it turns green, is there any way to see the flip coming before it happens? It turns out there is. Hidden underneath, every one of these systems leaks the same quiet signal before it goes. And once you know its shape, you start to see it everywhere. To see why a system jumps instead of slides, picture a ball resting in a valley. The ball is the state of the lake, and the valley is where it wants to sit. Give it a small knock and it rolls partway up the side, then rolls back down and settles. That is a stable state. It resists change and returns to itself. Now here is the part that makes the whole story. Many systems do not have one valley. They have two, side by side with a hill between them. One valley is the clear lake. The other is the green one. Both are stable. Both will sit there quietly if nothing disturbs them, and the lake can only ever be in one valley at a time. What the slow pressure does, the fertilizer year after year, is not push the ball up the hill. It reshapes the ground itself. The clear valley gets shallower, and the hill beside it creeps closer, and for years the ball just sits there, still stable, still looking completely fine, until the floor tilts far enough that the ball rolls over the hill on its own, drops into the other valley, and settles into green. That is the flip, not a slide, a fall from one valley into another, and it feels sudden because for all those years, right up to the edge, the ball never moved. Now you might think, fine, if we crossed a line to get here, we just step back over it to undo it. Take the fertilizer back out, and the green lake turns clear again. But that is almost never how these systems work. To get back, you usually have to go much further than the point where it flipped. Look at the two valleys again. To fall into green, the clear valley had to vanish. But now the ball is deep in the green valley, and green has its own hill to climb, its own feedbacks holding it there. The algae shades the plants die, the mud releases more nutrients, and green keeps itself green. Undoing a little pressure just is not enough. You have to push all the way back past a second, farther line, before it will flip the other way. The path in and the path out are not the same path. Scientists call this hysteresis, and it is why a tipping point is such a serious idea. It is not a dial you can turn up and back down. It is a trapdoor. The same shape shows up in an ocean current we followed in an earlier video, one that has two stable modes and does not simply switch back when you reverse the pressure. Cross the line, and getting home costs far more than the step that took you over it. So where exactly is the line? Let us watch the valley itself as the pressure rises. Start with a deep, safe, clear valley, the ball resting comfortably at the bottom. As the pressure climbs, the valley grows shallower, and the hill on the far side slides in toward the ball. Shallower and shallower, the walls flattening out. And then, at one precise value, the valley and the hill meet and cancel. The bottom the ball was resting in simply flattens into nothing, and there is no valley left to hold it. That exact moment, where a stable state stops existing, is the tipping point. Mathematicians have a name for it, a fold, but you do not need the name to feel it. It is the instant the floor gives way. The unsettling thing is how ordinary the last step looks. The pressure that finally erases the valley is no different from all the pressure before it. There is no special final straw that announces itself. The system passes the point of no return quietly, and only afterward, once it has fallen, do you see that a line was there at all. Which brings us to the real question. If the line is invisible, and the last step looks like every other step, what could possibly warn us? Here is the signal. It is not in where the ball sits, it is in how the ball wobbles. Go back to a deep valley and give the ball a knock. The steep walls throw it back fast. It returns to the bottom quickly, barely wobbles, and is still again in no time. Now take a valley that has grown shallow, close to the tipping point, and give it the same knock. The walls are gentle now, so the ball drifts back slowly, sluggishly, taking far longer to settle. That is the whole secret. As a system approaches its tipping point, it gets slower and slower at recovering from anything that disturbs it. The everyday knocks are always there. A hot week, a storm, a small shock, and near the edge the system takes longer and longer to bounce back from each one, so its wobble grows. It swings wider, and it swings more slowly, drifting instead of snapping back. Scientists call this critical slowing down, and it is astonishing because it does not care what the system is made of. A lake, an ice sheet, a forest, a power grid, even signals in a human heart before a certain kind of failure. Utterly different things, but as each nears a tipping point, the ground under its ball flattens the same way, and the recovery slows the same way. The warning is not written in the water or the ice, it is written in the shape of the valley, and the wobble is the shape leaking out. Now, a slower, wider wobble is something you can actually measure, and this is where it stops being a picture and starts being data. If you watch a system near its edge, 2 fingerprints show up in the numbers. Because it swings wider, the variance goes up, the ups and downs get bigger. And because it drifts back slowly, each moment looks more like the moment just before it, so the wobble becomes more sluggish and more self-similar over time. Researchers have found both of these creeping upward ahead of real transitions, in lakes pushed to flip in experiments, in ancient climate shifts recorded in cores, in stressed ecosystems. Source, Sheffer and colleagues, Nature, 2009. But I promised you the honest version, so here it is. This is not a crystal ball. The signal is real, but it is noisy, and it can lie. A system can flicker and recover without flipping, a false alarm. Some transitions give almost no warning at all. And most of the clearest cases were read after the fact, in hindsight, when we already knew the flip had come. Reading it live, in a real system, with the exact line unknown, is genuinely hard, and it is one of the most active questions in the science right now. The honest claim is not that we can predict the day, it is that these systems are not silent before they break. They slow down first, and slowing down is something we can learn to hear. Step back for a moment, and look at what we actually found. We started with one green lake, and underneath it we found a valley with a floor that can flatten. Then we lifted that same valley out and slid it under an ice sheet, a forest, an ocean current, a grid. The details could not be more different. The math underneath is the same. 2 stable states, a floor that flattens under slow pressure, a wobble that grows wider and slower as the floor gives way. One shape, wearing 1,000 disguises. That is what a systems view buys you. Not a prediction of exactly when, but a way of seeing that crosses every boundary. Once you know the shape of a tipping point, you cannot unsee it. You start to notice it in a fishery that empties, in a market that breaks, maybe even in the slow weeks before a big change in your own life. The sense that something is wobbling wider than it used to. The systems around us are not always as steady as they look, but they are not silent either. If you know where to listen, the quietest signal of all is a system that is taking a little too long to steady itself. And that, more than any single number, is how you see a flip coming.